we're looking at exercise 3J today, looking at using the inverse of a 2x2 matrix for transformations. So again, there's a few things that you need to be aware of about matrices, and again, not sure whether these were covered last year, but we'll need to have a chat about them. If you hear people talking about the identity matrix, basically it's a square matrix whereby the top left through to the bottom right, so the diagonal of the matrix, from the top left down to the bottom right, is some numbers, and all the other positions have zeros in them. When we talk about the identity matrix in maths, we use an I to represent an identity matrix. Again, if you've got some matrices A and B, and they are square matrices, that means they have the same number of rows as columns. So that, yeah, they have the same dimensions, and both of them have the same dimensions. They're both the same size and square. It should be noted that if you multiply the two of them together, they will work the same way. If you multiply A by matrix B, it is the same as multiplying matrix B by matrix A. Often the order is important, but if they are the square matrix and they have the same dimensions, then in this particular case, if you can multiply them and they come out to both being an identity matrix, then you can say that A is the inverse of B and B is the inverse of A. But only if you multiply both of them, it comes out to being an identity matrix. Again, if you have a square matrix A and it has an inverse matrix, then what we usually write it as is A to the power of -1, or inverse of A. So that notation should be no surprises there. It says here a square matrix is said to be regular if its inverse exists, and is said to be singular if it does not have an inverse. Now, again, here is how you go about getting the inverse of a 2x2 matrix. By hand, you would only ever be asked to get the inverse of a 2x2 matrix. If you had to do something larger like a 3x3, etc., etc., then you can use your CAS calculator to do that. You'd pop in the matrix, go do its inverse, so do the matrix to the power of -1, and it will work it out for you. But by hand, we can really only do in this course a 2x2 matrix. So again, consider this matrix here. We've got matrix A. These are positions, or these positions are denoted by A, B, C, and D. So in order to get the inverse of A, what you need to do is work out 1 over AD take away BC. So 1 over A times D take away B times C. So that's out the front there. And then our matrix, we are multiplying it by the matrix, but we're swapping some values around. The A and D swap positions. So you can see the A goes down to this position, the D goes up to this position, and we take the negative of these ones over here, negative of the B value and the negative of the C value. So we multiply it by negative. So again, basically it swaps the sign. So if these are positive here, they become negative. If they were negative here, they become positive. This value underneath here, the 1 over, this A times D take away B times C is also known as the determinant. Whether you are asked to work out the determinant of A, or whether you see DET of A, it just means find out the determinant of A. It's this part here, A times D take away B times C. Cool. It says here in a 2x2 matrix, A has an inverse if and only if the determinant of A is not equal to 0. So again, with these things, if you're asked to find out the inverse, it's often wise to work out what the determinant is first. If you work out the determinant and it is equal to 0, then there's no point going on and trying to find out the inverse. It's not possible. The determinant has to be a value that's not equal to 0. Alrighty, so let's have a look at example 27 here. Cool, it says for the matrix A here, find the following. Find the determinant of A. So again, there's a rule for the determinants. A multiplied by D take away B times C. We know that's A, that's B, that's C, that's D. It's a matter of just plugging those values in, and we find out that it equates to 16. Once you have the determinant, it's a little bit easier to work out the inverse. Remember to find out the inverse of A. It's 1 over the determinant, so we already worked out what the determinant was in the previous question. It was 16. So it's going to be 1 over 16 multiplied by the matrix, changing these values here. So these swap around, the 3 and the 6 swap positions, the A and D have swapped, and also the signs change on these ones, the B and the C value. So that was positive here, so it becomes negative, and likewise this was positive, it becomes a negative. Cool, we found out the inverse there. Next, it says here, find out x if ax is equal to this one here. What needs to happen is basically we need to get rid of this a to find out what x is. So what we're going to be doing is we're going to be multiplying this side of the equation, the left-hand side of the equation, by the inverse. So when you do the value, the inverse of a multiplied by a just becomes the identity. So it basically gets rid of it. And so in this particular case, we're going to multiply the left-hand side by the inverse of a. So that'll get rid of those, and you'll just be left with the x on the left-hand side. If we multiply the left-hand side by the inverse of a, you have to do the same thing to the right-hand side of the equation. Now here's where it's important. Because we are multiplying the matrix A by the matrix the inverse of A, notice we're doing the inverse matrix first, multiplied by just the original matrix. You have to do it in the same order on the other side. So notice here we did the inverse matrix first. We're going to multiply the inverse matrix first over on this side, because remember the order in which we multiply matrices is important. Okay, so the good news is we had already worked out what the inverse of A was up here. We've substituted that in. It's going to be multiplied by this here. Simplifying things down, we'll need to multiply these two matrices. We can do the multiplication. It simplifies down to this here. You still got the 1/16 out the front. Essentially, here is multiplying by 1/16 is essentially the same as dividing each of these by 16. So you can go ahead and divide each of these by 16. It simplifies down the matrix here. Last but not least, it's asking us to find out y if ya is equal to this. Again, in this particular case, notice the a is the second thing. So we're going to be multiplying after this a by the inverse of a. So with this one that we did over here, a was the first thing, so it's a multiplied by x. Because it was the first thing in this one, you would multiply by the inverse first. And this one here, a was second, so we're going to multiply it by the inverse of a after that. So it's after the y. So doing that, remember you need to do it both sides, which is what we've done here. Simplifying things down, and then obviously from here dividing by 16, simplifying these fractions down. Cool. Alrighty, there's a note. It says here, if a transformation is defined by a matrix in the form matrix A is equal to, notice here we've got some values in the diagonal, A and B, and the rest are all zeros. It says if these values A and B are not equal to 0, then you can quickly work out the determinant. It's just going to be these values, A multiplied by B. You don't have to worry about those. Likewise, it's very quick to work out the inverse of A. It's just obviously 1 over the A value in this position and 1 over the B value in this position, the rest are zeros. So this can be useful if it's diagonal from left to right this way. So that's a bit of a shortcut there. It says worked example number 28. We've got a matrix defined like just above. It says find the equation of the image of the graph, the quadratic equation under this transformation. Cool, so like we were doing before, transformations map as follows. Using the matrix notation, obviously we've got the matrix multiplied by the original x and y values is equal to the new x and y values. Again, if we were thinking of it as in matrix equations, this here could be denoted as matrix A multiplied by matrix X. and we could denote this as matrix X dashed. Again, if you think about rearranging things to solve, if you wanted to get rid of this A here, you would have to, and it's before the X, you would have to multiply before this A by the inverse of A. And then as we did it on the left hand side, we did it before, you have to multiply by the inverse of A before this one here. So that cancels out there. And over here we've got X is equal to the inverse of A multiplied by X dashed. So you can actually then go back and do the calculations. Here is the X matrix. Here is the inverse of A. Again, we looked before, because it was just some A and B values, we know that it's going to simplify down to its inverse is just 1 over a third up here, and 1 over 2, sorry, 1 over a third, 1 over 3 up here, and 1 over 2 down here. So that's there, and multiplied by the new values. Again, you can multiply this out, it comes to 1/3 X dashed, and on this line it's 1/2 of Y dashed. So again, writing it out, X is going to equal X dashed over 3, and Y is going to equal Y dashed over 2. Substituting those into the equation and then rearranging, you get the equation. Cool. And it says here, and it does, oh sorry, I should have scrolled down a little bit there. You can see what it comes out to being. It does make a note here, it says this makes quite hard work of an easy problem. Yep, you could have done a lot easier, but it demonstrates that a procedure can be used to use transformations to find by a 2x2 non-singular matrix. Alrighty, last one I want to go through. It says here, a transformation is described by the equation. Perfect. We've got matrix A and we've got matrix B. Find the image of the straight line with the equation y equals 2x plus 5 under this transformation. Alrighty, it says first solve the matrix equation for x. Alright, so we're going to need to rearrange things and get x by itself. So in this particular case, we need to get rid of this A. It's the thing that's being multiplied at the start. So we need to multiply by the inverse of A in front of that. So that will eliminate that. From the left hand side, because we multiply by inverse A at the front before it, we need to multiply in front of X dashed over on this right hand side. Yep, position is important. That's gone there, so you're just left with X plus B, and on the right hand side we've got inverse of A multiplied by X dashed. Again, you've got this B we want to move, take away B from this side. Once we've got it set up like that, we can put in the matrices that we're working through. So again, matrix A, you have to work out the inverse. So they haven't shown the step here, but obviously it's 1 over the determinant multiplied by the matrix where you're changing those values. It comes out to this here, this part. That is multiplied by the new values matrix, which is here. Take away B, so take away 1 over 3, sorry, 1 and 3 in the matrix. Again, from here, it's a matter of simplifying this down. We multiply these together, you end up with what's listed here. Like the other question as well, you can write down what each of these values are. X is equal to this, and Y is equal to this one here. Plug those into the straight line equation, rearranging, and you get the final equation there with that. Please note there's a bit of a summary section here that just articulates these things that I've spoken about. Be worthwhile having a look at those. Thank you very much for listening. I hope you have a good day. Enjoy the maths. Bye for now.